In this lesson, we discussed the concept of general model that is used in spread spectrum communication. And when we talk about the general model, which we have already seen, but for the sake of this lesson, we wanted to highlight it, is that the input data is fed into the data encoder. So here we have zeros and ones. This is converted to become line code. That is, you might have non-return to zero polar or bipolar non-return to zero. So this is now the pulses that you can be able to determine. You can be able to know that if it's a 1 is a positive pulse, is a 1, negative pulse is a 0. So looks like I have lost it. 1 0 0 1 0. So this is our input data of 1 0 0 1 0. So this is what the data encoder does, produce these pulses. So this is what we are able to get at this point. But now, for us to perform or to achieve the spread spectrum, you have to take it through the spread spectrum modulator that receives the spreading code from the pseudorandom noise code generator, and the multiplication is done. And therefore, what we are saying is that the signal that comes in here is at the rate of RC, which is equivalent to 1 over TC, where TC is the chip duration. So this is the signal that we receive at this point. So here we have the pseudorandom noise code that is modulated by our input data, your spread spectrum code. This is the signal that is now sent to the wireless channel, and at the receiver side, we have the signal that is spread in spectrum, and that signal may have been influenced by an interference, and that interference we are going to observe in the subsequent slides. How when we apply this spreading code, it's spread, and therefore its effect is reduced or minimized, and therefore we are able to recover our data pulses. These pulses, again, we are able to receive them in terms of this one at this point. This is the kind of signal that we receive at this stage, and this data decoder is the one that generates for us our binary data stream, which is in the form of zeros and ones. So we will observe some few points here, and what we have just said about that is that the input data is fed into the data encoder that we have seen. In the work of the data encoder, we have been able to see it generates the data pulses. Then the encoded signal is modulated using the spreading code, which is generated by the pseudorandom noise generator. Then on the receiving side, the same spreading code is applied, and this is the code that kind of spreads the interference, and the interference effect is reduced on our received data, and we are able to recover it. And finally, the modulated signal is passed through the data encoder to recover the original data output, which was sent in form of binary zeros and ones. Now we look at that process in more diagrammatic. We want to see how the signals look like in terms of the frequency domain. What we see is that the frequency of our signal is this much. So this is your information signal that you are transmitting in frequency domain. So remember, our information is in zeros and ones. But now when you convert this signal that we are sending in terms of pulses, in the frequency domain, you see that there's a bandwidth requirement of FB. This, when it's taken through the spreading process by the spread spectrum modulator, we get a spread spectrum signal that is increased in bandwidth that we can now call FC. And the bandwidth of this spread signal is way bigger than required. We are seeing the channel that we are transmitting through may be a wireless channel. Just we had seen that it requires the bandwidth to be of value FB. But when you do the spread spectrum, we increase that bandwidth to FC, which is way bigger than the minimum required. But this spreading is the one that gives us the advantage of being able to mitigate the effects of interference and jamming. At the receiver side, we do the spreading process. We apply the same spreading code. That spreading code removes the effect of the earlier pulses. The spreading code that was encoded or modulated by the data stream, and we are able to receive our signal back in its original bandwidth of FB. And we might have noise interference here that is spread, but then we apply some filtering action that just cuts off any bandwidth bigger than our FC or FB, and therefore we are able to receive our transmitted data. So in summary of what we have said is that one, the narrowband information data signal is converted to a wideband spread spectrum. That we have seen that we start with a small or narrowband data signal, and it is spread in frequency, and therefore it is transmitted in the wireless channel. The received spread spectrum is again spread at the receiver side through the spreading process. Then I have already said that the same spreading code that was used in the transmitter is used at the receiver, and the effect of the spread spectrum modulation is to increase the bandwidth or the spectrum of the signal that is transmitted, so that it is able to withstand the effects of interference and jamming. Now we want to talk about a concept, processing gain, and we ask ourselves, what is the processing gain? And we say that it is defined as the gain in signal to noise ratio, which is obtained when you perform the spread spectrum modulation. And this gain represents the gain achieved by processing a spread spectrum signal over an unspread spectrum signal. Just like we have seen, we have the unspread and we have the spread. So if we say this is our graph that we have seen in our previous slide, we say this is your unspread signal, whereas the spread signal is this one. So when you take the bandwidth FC, if we say that the bandwidth of the spread signal is given by BWZ, and you divide by the unspread signal, which is BW, then this is the gain that you achieve, that is called the processing gain. So we say that it is an approximate measure of the interference rejection capability. The bigger the gain, the better spread signal is able to reject the interference that may be introduced when the signal is transmitted through the channel. So we may be able to figure out how the processing gain is achieved, which we might also see that as we have said that the bandwidth divided by BW is our processing gain, G, we can be able to say that this is equivalent to FC over FB, and we have already seen that FC is 1 over TC and FB is 1 over TB. So with this becomes in this form, we consider the gain can be given by TB divided by TC, and TB is this duration of your pulse. This is your pulse period, but then the spreading code is having very many pulses of zeros and ones that are produced from the spreading code of which is combination of ones and zeros. So we have already said that the chip rate, which is the rate at which the spreading code is arriving, is determined by 1 over TC, and TC is just this one period here. So this is the one that is shown here, or the chip period or chip time. So we have said that that is how you obtain the gain, which is sometimes referred to as GP. And if you want to have a higher gain, because we cannot interfere with the TB or the bit rate, we can only reduce the TC, which is the reciprocal of chip rate, RC. So if you increase the chip rate, then you are going to be able to get a higher gain. And number two, if you increase the number of bits represented in the PN sequence, then, for instance, N was equals to 15. If you increase this one to become N is equals to 30, definitely that doubles your processing gain. That is another way in which you can be able to achieve a higher processing gain. So as we have seen, this is how you are able to obtain the processing gain, which you have said is equivalent to RC divided by RB, because these are the reciprocal of each other. And we have already defined these two terms. The chip duration is the length of time that one bit pulse of PN sequence takes. And we have already said that how we can increase the processing gain is by reducing the chip duration or increasing the number of bits in the PN sequence. And we have also now seen from the transmitter, we are transmitting this spread spectrum signal that is having bandwidth of BWC, but then along the channel some interference may be introduced, and therefore at the receiver we may not be able to recover our spread signal or spread spectrum signal correctly. So what we need is to be able to remove this interference. So what we do when we multiply our spread spectrum signal with our spreading code at the receiver, what happens is that another spreading happens. So in this case, what is spread is the interference, but now our original signal that was transmitted is the spread. So by doing that, what will now follow here shortly is that we are going to do a filter that is going to cut off, because this is the spectrum of the interference, BWI, and between these two is the spectrum of BW signal that you have transmitted. So you are going to apply a bandpass filter that will just limit your received signal to the bandwidth BWC. And therefore, the one that is coming from the interference is cut out because it has already been spread by the second spreading code. So we have said that the filtering action that we perform at this stage removes the interference signal or reduces its effect to very minimal levels. So in summary, we said now that the bandwidth signal is reduced to BS while the interference energy is spread over another bandwidth that is. So this is what I was calling BWI. This is BWB that we are receiving, and we are saying that now you're going to apply the filter that will just limit the received signal to only this frequency range, and whatever else which is being covered by BWI or BSS is cut out. So the filtering action of the demodulator removes most of the interference spectrum, and that does not overlap with the original signal that we have seen, and that the most of the original interference energy is eliminated or its effect is minimized. In terms of now the terms that we have used, we have said that the processing gain is given by BWC divided by BWB. So these are the terms that we are going to be using interchangeably. We have already seen that this is how you define the processing gain. Where BSS is the spreaded bandwidth, we have already said that this is the spreaded bandwidth, which is the BWC or spreaded bandwidth, and the BS is the signal bandwidth. We have already seen this diagram. Say you are setting two bits. The one is 1, this is 1, and the other one is 0. So what will happen is that if your spreading code was 1, this 0, 0, 0, 1, 0, 0, and 1, 1. This might be your spreading code PN, and you're setting a symbol 1. Then if you're setting a symbol 0 in the next bit duration, which should be here, all these are going to be reversed. So instead of now this being 0, 0, 0, they're going to become 1, 1, 1, but now they are going to be on the opposite side. Then this becomes 0, 1, 1, 0, 0, 0, 0. So these are going to be interchanged. The only thing I have not drawn them as though they're interchanged, but in actual sense, if you're setting a 0 and here you're setting a 1, the way they were when they are 1, they would be opposite of how they are when you're transmitting a simple 0. So we'll see now some salient features of spread spectrum digital communication system, and one of them is, okay, these are can be see to be the advantages that the spread spectrum offers in comparison to the normal narrowband communication. Number one is that it offers immunity to jamming. So we say that the spread spectrum signal are difficult to detect on a narrowband receivers because the signal's energy is spread over bandwidth of 100 times that of the information bandwidth. So that is one. The receiver or the jammer might only know the bandwidth of your information signal, but when you said 100 times signal in terms of bandwidth, you don't know where to attack from. So you're saying that you were expecting this size, but you are saying something this size, so it doesn't know exactly where the signal lies. Number two, there is so low interference, and we say that the spread spectrum signals are less likely to interfere with other narrowband radio communications due to the spread of energy over wideband. Because the other signals are narrowband, they may not be able to interfere with a wideband spread signal. We also say that we are able to achieve high processing gain, and we have already defined it as the ratio of the transmitted RF bandwidth to that of base bandwidth of the spread signal. So another advantage or salient feature that is offered by the spread spectrum is that of encryption. It is very easy to encrypt your information signal, and we say that only a receiver having the knowledge of the spreading code that you are using can be able to recover the information that has been encoded using spread spectrum. And for that reason, it provided higher security or greater security, which makes it impossible for someone to exploit or spoof your signal. And we define the signal exploitation as the ability of a desired interceptor to use your information. So someone may, when they are able to exploit information, they might use it. But with the spread spectrum, that makes it impossible for someone to exploit your signal. There is another concept we are defining, we are saying here as spoofing. And we say spoofing is the act of maliciously sending misleading message to the network. So again, by the virtue that your signal energy is spread, a spoofer may not be able to inject in an intended or misleading message because it is going to be considered as interference, and we have seen that interference is going to be spread when it is received on the receiver side, and its effect is going to be minimized. Again, we say that it offers multiple access, in which case several users can independently use the same higher bandwidth with very little interference to each other. This property is very much commonly used in CDMA cellular communication applications. Finally, we talk about how this concept of spread spectrum is used in real world, and one of the most common one is it was used in North American CDMA, in which case it provided very secure second generation digital cellular communication standard. And you remember 2G for us was offered by GSM, but in North America, that is USA and Canada, they were using the standard that was utilizing the spread spectrum, which I believe is still being used up to now for the 2G voice communication. Another example is it is in wireless LANs or Wi-Fi. Most of them are using the spread spectrum to provide security, and therefore the interference is reduced, and as well as the many advantages that we have seen with the spread spectrum.